So far in this course, we have spent a considerable time with bag of words based retrieval approaches. These approaches fundamentally rely on exact keyword matching between queries and documents. Now, this creates a significant challenge that we call the vocabulary mismatch problem that we have already introduced. Let us illustrate this with an example. Imagine the user has come to the system, a retrieval system, with this query: how to care for a feline pet. And one relevant document in our collection discusses a guide to cat health care. Now, despite discussing the same concept, these two texts, that is this query Q and the relevant document D, is not having any term overlap here. As a result, our traditional bag of words based retrieval models, which considers exact term matching, will show zero term overlap, causing this highly relevant document to never been retrieved. The fundamental issue is that these methods cannot capture semantic similarity. They only recognize literal word matches. We did discuss relevance feedback as was one solution, but those feedback based approaches were also considering the exact word overlap, right? They were just increasing the size of this query such that more overlap can be made possible. So we are left with this crucial question: is there a more direct way of capturing the meaning itself rather than just matching surface level terms? So how do we address this challenge? One approach, as I have mentioned, we have discussed already, is query expansion, adding words having similar meaning to the query for better retrieval. If we have the query vehicle smoke pollution, this might mean expanding the query to include terms like automobile, car, fuel, exhaust, smog, toxic, etc., or other semantically related terms. But this immediately raises the crucial question: how do we actually find these similar words in a systematic and principled way? We need a method that can automatically discover semantic relationships between terms across our entire vocabulary. So far in this course, we have discussed some statistical methods to find these words, like Rokio and relevance based language model. These were important first steps. They showed us we could actually use feedback and collection statistics to improve our queries. But these methods also works on the basis of term overlap. We were only expanding the query with more expected semantically similar words, but the term selections were happening based on some statistical co-occurrences. Now, what if we could go deeper? What if we could capture the fundamental actual semantical meaning of words themselves? This brings us to our main topic of discussion for this lecture: embeddings. First of all, what exactly is embedding? Fundamentally, it's a dense, low-dimensional vector that represents an object, whether a word, sentence, or document, in a continuous vector space. This represents a major shift from the sparse high-dimensional representation we were used while making the term document incidence matrix. Remember our early approach, we represented a document as vector in an n-dimensional space where each dimension corresponds to a term from the vocabulary, and the value indicated that whether the term is present or absent, or later on we moved on from only 0 and 1 to store the weights as well. So those were actually very much sparse matrix. Now we are thinking of doing something in a dense manner. Now instead of that maybe 1 million dimensional one hot vector representation where most dimensions are 0, we work with a dense, maybe let's say 300 dimensional vector where every position will be carrying some meaningful information. The key insight here is that similar words should be close in this vector space. The core idea is representing every word as a low dimensional vector in an abstract space. But it's not just about grouping similar words. We also want the similarity between those vectors to directly reflect the semantic similarity between terms. Also, it would be nice if the vector offsets between words can actually encode meaningful relationships. The vector from, let's say, Germany to Berlin might be similar to the vector from France to, let's say, Paris. So it would be nice if the vector can, if the embeddings can also represent this. This is kind of capturing the capital city relationships, capital country relationships. Further, it would be nice if the conceptual composition can be observed through simple vector arithmetics between the embedding of the words. For example, can we perform operations like adding the vectors for German with the vector for airlines and find that the result is very close to the vector for Lufthansa? In short, the embedding that we want to make should made in such a way such that the words that occur in similar context should be having similar meanings. The embedding model should learn that if two words are interchangeable in sentences, they probably mean similar concepts. Now, to summarize, we should embed all the vectors to make word embeddings where each word becomes a fixed length vector, typically with, let's say, 100, 200 or 300 dimensions. The core hypothesis is actually dating back in 1957, is that words that occur in the similar context have similar meaning. Now, considering this hypothesis and those analogies to capture, several techniques were proposed to make word embeddings. A detailed discussion on word embeddings is beyond the scope of this course. We will briefly mention some of these embedding models which are popular and effective. So, how do we actually create these embeddings? Very briefly, the most common approaches use neural networks that trained on massive text corpora. Word2Vec, introduced by Thomas Mikolov and colleagues in 2013, offers two main architecture: CBAO or Continuous Bag of Words model and skipgram model. CBAO predicts a target word from its context, while skipgram does the reverse, predicting context word from a target word. Another variant to generate word embedding is called using GLOVE, which was proposed in 2014. GLOVE uses global word-to-word co-occurrence statistics across the entire corpus and factorizing a massive co-occurrence matrix to capture direct statistical relationships. But our information retrieval task is a bit different. Here we have vectors for individual words, right? For every word in the collection, we have a vector associated with it. But in information retrieval, it deals with queries and documents, which are sequence of words, not a single word. And we need to compute the similarity between query and document. So, how to represent a sequence of words in the vector space? In other words, how to create a vector representation for the query as well as the documents. A simple solution is averaging. We can take the average of all the word vectors in a sentence or document to make the sentence embedding or the document embedding. We can even use TF-IDF like weights to give more importance to significant terms during averaging. However, this approach has a major limitation. Consider these two sentences: the cat sat on the mat and the mat sat on the cat. They have identical word content, so they would just be having identical vector representation if we just average them. But meaningfully, we can understand semantically they are completely different. So the critical issue is that we are losing the word order information by doing this simple averaging here. This brings us to more advanced sentence and document embedding techniques designed specifically for handling sequences. Infercent uses supervised learning on natural language inference data to encode sentences into single vectors. The Universal Sentence Encoder, or USE, from Google, this is proposed by Google, employs a transformer architecture for general purpose sentence encoding or general purpose sentence embedding. For document, that is to represent a document as a vector to make document embeddings, doc2vec extends the word2vec idea by including document level vector. More recently, BERT based approaches use the special CLS token output or average all the output tokens to represent a longer text. We will explore the application of BERT in IR in the next lecture. So how do we actually use embeddings to improve information retrieval? The first major application is semantic search. Basically, we will be replacing the traditional term matching with semantic similarity. The process involves three key steps. First, we will be converting every document into document vector. Second, we convert the user's query again into a query vector. And third, we will rank documents by the similarity between the query and the document vectors, typically let's say using cosine similarity. This means that feline pet can now successfully match documents about cats because their vector representations expected will be kind of similar in the semantic space, even though the words themselves are entirely different. The second application is you can call intelligent query expansion. Instead of using statistical co-occurrences, we can use word embeddings to find most semantically similar words to each of the query terms. For each term in the original query, we find, let's say, k most similar words in the nearest neighbor in the embedding space and add these semantically similar words in the embedding space to the query. For example, with the query, let's say Python error as the original query, we might expand this query to include terms like, let's say, exception, bug, fix, troubleshooting, program, etc. to this original query. So all these words are actually semantically related to this original query. And after expanding this, applying this expanded query for retrieval, expected the performance will be improving. The third application is re-ranking, which is a hybrid approach that leverages the strength of both traditional term overlapping based approaches as well as this kind of embedding based approaches. In the first stage, we use a fast traditional methods like BM25 to retrieve a large candidate set, let's say top 1000 documents. This ensures that we have kind of a good recall. Then in the second stage, we use more computationally expensive but powerful embedding based models with considering the embeddings of the words to re-rank these candidates, these candidate documents. This improves the precision by bringing the most semantically relevant documents to the at the top, resulting into a better precision. This two-stage process gives us the best of both the worlds, as I have mentioned, the efficiency of this traditional IR-based model and the semantic understanding of this embedding-based models. Taking this further, we have dense retrieval system with dense passage retrieval, or in short known as DPR. This uses only the dense embedding for first stage retrieval. In DPR, we have separate encoders for documents and queries that convert them into dense vectors. All document vectors are pre-computed and stored in a specialized index. And at the retrieval time, we encode the query and use first maximum inner product search this over the dense vectors to find the closest documents. This represents a true paradigm shift from the sparse to dense first stage retrieval. Now an important question is, how do we evaluate these embedding based approaches for information retrieval? Now as the task is still retrieval, document retrieval we are considering, we can use the same evaluation metrics we have already discussed. That is, let's say P at K, recall, map, NDCG, MRR and so on. We typically see the biggest improvement on queries which are suffering from vocabulary mismatch and on complex conceptual queries where understanding meaning is more important than mere matching of the some specific terms. However, applying embeddings for information retrieval have some limitation or challenges as well. First of all, the computational cost. This training and inference of these embedding models are much more expensive than simple word overlapping based approach such as BM25. Another major issue is interpretability. It's hard to explain why a particular document was retrieved at some top position when we are dealing with, say, some dense vector similarities. We also face out of the vocabulary situation when we are encountering some words during retrieval which we haven't seen during indexing. There is also another issue that we can face is domain adaptation issue. Where let's say we are using Wikipedia for training of the embeddings and we are applying that embedding in some other domain, and there may be some term mismatch or term non-overlap between the Wikipedia collection and the domain in which we are applying that learned embedding. Another limitation we can face is the biases, where embeddings can actually amplify some societal biases present in the training data. In practice, the most robust solution often combines traditional and embedding based methods in a hybrid framework. By combining, let's say, sparse BM25 scores with dense embedding based similarity, we get high recall from the sparse component and high precision from the dense component. This hybrid architecture has become the modern standard in production retrieval systems, balancing the efficiency based on sparse, let's say BM25 based similarity with semantic understanding captured by this embedding based component. Now, how to actually apply these embedding based models for information retrieval? Fortunately, we don't need to implement everything from scratch. There are excellent tools available for working with embeddings. For word embedding, GenSim provides easy to use implementation of Word2Vec as well as Glob. SpaCy provides pre-trained word vectors. For sentence embedding, the sentence transformer library offers state-of-the-art models, and Hugging Face transformers provide access to BERT and other advanced architectures, which we will be discussing in the next lecture. For dense retrieval, Facebook AI Similarity Search offers efficient similarity search, which is basically a library, this FAISS. This library offers efficient searching algorithm, searching mechanism already. We can simply import them and we can use them. And Elasticsearch, a variant of or an extension of Lucene, now includes KNN plugin as well. This actually enables vector search to be performed for retrieval as well. Now let's look at some practical code. Using the sentence transformer library, we can load a pre-trained model, encode a set of sentences, and compute cosine similarity between the encoded text. The code shows how straightforward this can be, just a few lines of code to load the model, encode our text and compute the semantic similarity. here. So in this code, what I am doing is I am encoding 3 sentences. This sentences list is containing 3 sentences, the 0th index, 1th index and 2th index. The cat sits on the mat, a feline rests on the rug, programming in Python is fun. So we can understand as a human being that these two are related, but there are no term overlap between these two sentences except for this stop word here, on. Now after encoding the set of sentences, what I am doing is in this 19th line, I am calling this cosine similarity function, which is defined in this sklearn. Here I am providing 2 parameters. Parameter 1 is the sentence with which I will be computing the similarity, and the parameter 2 is the set of or list of words, a list of sentences with which I will be computing the similarity of this word 0 or sentence 0, that is the cat sits on the mat. So this code, this line will be computing similarity between the cat sits on the mat with a feline rests on the rug and the cat sits on the mat with programming in Python is fun. So after doing this, if we compute the similarity, we will be seeing, although there are no term overlap between 0 and 1 except for this on, which is a stop word, we will be observing a high similarity between the cat sits on the mat and the feline rests on the rug, and we will be observing very low term overlap between 0 and 2. So this is possible because this model that we are incorporating, using which we are encoding these 3 sentences, is actually capturing, is actually containing the information that cat and feline are kind of semantically similar. As a result, when we are encoding these 3 sentences in 3 different vectors as 3 different vectors, their vector representation, that is for this and this, will be much more similar or much more close to each other in the vector space. Here we have another extended example. We are using the same sentence transformer pre-trained model. Here we have 4 sentences. Sentence 0, I love programming in Python, which is related to programming language. 1th or the sentence stored in the 1th index, the Python loves to eat frogs, which is related to snake. 2th or the sentence stored in the 2nd index of the sentences list, it is better to write in C than scripting languages. And this 3rd index containing the sentence, I love daydreaming, which is entirely unrelated. So we have 4 sentences, first related to programming language, next snake, 3rd programming language, 4th is entirely unrelated. And then what I will be doing is I will be computing the similarity between 1 and 2, then 1 and 3 and 1 and 4. This is we are doing inside this for loop. And if we look at the output, we will be seeing that the similarity between the sentences I love programming in Python and the Python loves to eat frogs is actually 0.32. It's not that much. Although there is, as it is containing Python and Python is a meaningful word, that's why it is having still 0.32 is not very small similarity, but it's still comparative to this is small. Now if we provide a long sentence here with programming Python and a long sentence with Python snake, we will be getting much less similarity here. As the 2 sentences that we are considering is small in size, this term Python is actually getting some weightage based on which it is getting some amount of similarity still. Now if we compare the first or this I love programming in Python and it is better to write in C than scripting language, as you can see there are no term overlap between these two, this and this, except for this in, again stop word. Still you will be finding the similarity 0.047, which is significantly better than or significantly bigger than this. And finally, when we compute the similarity between I love programming in Python and I love daydreaming, so we can understand it is entirely unrelated semantically, but I love, this phrase is actually present, overlapping between these two sentences. Still, you will be finding that their cosine similarity after encoding them in that, using that encoding pre-trained model, you will be finding their similarity much less. Let's summarize our key takeaways from this lecture. Embeddings are dense vectors that capture semantic meanings. This directly addresses our vocabulary mismatch problem that we have introduced while talking about the bag of words based approaches, bag of word based retrieval approaches. We can create embedding for words, sentences and documents, enabling three major applications: semantic search, applying them in the query expansion, and as well as re-ranking. Now, dense retrieval represents actually a paradigm shift towards a fully neural retrieval, while hybrid approaches combines actually the sparse and the dense methods, often to provide the best robust performance in terms of information retrieval. In the next lecture, we will be discussing another major advancement that comes with transformers and BERT. These models generate contextualized embedding, where the same word can have different vector representation depending on its context. So, bank in river bank versus the investment bank will be getting different vectors. So, we will be discussing transformers and BERT based models in the next lecture.